All right, so number 11 is a little bit different of a problem. It gives you a table and a coordinate plane, and then it has a bunch of options as to what possible equation could match up with this table. So for starters, I would definitely graph whatever you've been given. So -4, -8. I drew -8. You don't have to. -2, 0, 0, 4, 2, 4, and then 4, 0. All right, so we know that it's going to be shaped something like that. Okay. Now, a couple of things you want to take notice of is all these equations have 1/2 in front, so that's just kind of trash. You don't need to know about that. Or not that you don't need to know about that, but if they're all the same, then we know that the width of this graph is the same. So nothing changes, so that doesn't affect anything. But what we do see is that it's down like a frown, right? It's a negative shaped parabola. So that means we can automatically get rid of all of our positive equations. So A's out of the question and D's out of the question. Now, if you remember, these are our important points. They're when x is equal to 4 and when x is equal to -2. Well, how do I make x equal to 4 and x equal to -2? You remember it's the zero product property. So if I have x is equal to -2 and x is equal to 4, I can set them equal to 0 to find out what these factors are, right? So by moving them to the other side, I would get x plus 2 equals 0, and x minus 4 is equal to 0. The zero product property works both ways. So this must be our factors. We need x minus 4 and x plus 2. So this one's out of the question as well. There's our answer B. Okay? You see how we take it apart and put it back together and do all sorts of different things to find everything out about this problem. Number 12 is going to do radical expressions. Radical expressions is just simplifying a radical, right? What perfect squares can I pull out of a radical to simplify it as much as I can? Once again, we're looking for 4, 9, 16, 25, 36, 49, on and on, 64, 81, and so on. What perfect squares can I pull out of this one? Well, the first one that I see, remember, I don't have to pull out all the perfect squares at one time. I can pull out whatever I see. I know that 8 is divisible by 4, so I know for a fact that I can turn this into 4 times 20, right? Because 4 times 20 is 80. Nothing changed. I still have the square root of 80, and I have the square root of 4 times 20, right? So I can also turn that into the square root of 4 times the square root of 20, which means that I know what this is. That's 2, right? The square root of 4 is 2, but positive and -2 times the square root of 20. Then I look back in here and I see that I can pull out another 4 because I know that 4 times 5 is equal to 20. So I'm going to pull out another 4. So this turns into the positive -2 times 4, or times the square root of 4 times the square root of 5. And I know that this is 2, and every action in between here has been multiplication. So I'm going to take this outside number and multiply it by this new 2. So I get positive -2 times 2 times the square root of 5. Or I'll get positive -4 times the square root of 5. Now, can I pull out a 4, 9, 16, 25, any of that from the square root of 5? No. So I'm done. If you look back and you say, but Mr. Turner, couldn't you have pulled a 16 out of 80? Yes. Yes, you could have. You could have done that and it would have been a lot fewer steps, but that's just what I saw at the beginning. And don't forget that you can pull out as many perfect squares as you can all the way until you can't do it anymore. So this would be our answer. Positive -4 times the square root of 5. Number 13. Number 13 says the square root of 252. The first thing I like to do is to check to see if that's a perfect square in my calculator. How do I do that? I say the square root of 252. I hit enter, and no, it is not. Okay? So now I'm going to take 252 and I'm going to divide it by, I don't know, something in there. I know it's not 25 because it would have to be 250. It could be 36. It could be 49. I want to try something big just to see if it is. So I tried 36. I didn't know that before we started, but I know that 252 now divided by 36 gives me 7. So I'm going to split this up into the square root of 36 because that's the perfect square times 7. I'm going to break these up into two different houses, the square root of 36 times the square root of 7. The number is still the same. Nothing has changed. We've just been manipulating the problem. And I know that the square root of 36 is positive negative 6, and then it's going to be times the square root of 7. I know I can't pull in a 4, 9, 16, any of that out of the 7, so I'm done there. Number 14. The quadratic function has a 0 at negative 1 and 5, and its graph contains the point 0, negative 2. So, number 14, it says the zeros are at negative 1 and at 5, and it goes through the point 0, negative 20. Well, we can type that into stat, and it will give us an equation. Do y'all remember how to do stat? You hit stat, you hit edit, and you change. Let's see. Gotta delete all this stuff real quick. And you create a new table. So our table is going to be negative 1, 0, 5, 0, and 0, negative 20. You remember I need at least 3 points to make this work. So luckily I have 3. All right. So I'm going to hit stat, calc. This is a quadratic regression, so number 5. Enter, 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 all the way through. That's going to give me y equals 4x squared minus 16x minus 20. So the main thing I want from this, because I have a bunch of options, is I wanted this value up front. I wanted that positive 4. I know I can pull a positive 4 from this thing. So if you look at our options for number 14, B and D are out of the question because those are both negative 4s. So A, B, C, and D. B and D are out of the question because they say negative 4 up front. That's all I wanted from this whole stat, right? Now I'm going to use that zero product property to find out what was going on inside of everything else. So I know that x is equal to negative 1 and x is equal to 5. I'm going to use kind of the reverse of the zero product property by subtracting 5 on both sides of this one and adding 1 to both sides of this one. And I will get x plus 1 equals 0 and x minus 5 is equal to 0. And those are both of our factors. So I'm looking at A and C now to see if one says x plus 1 and x minus 5. Let's see. X plus 1 and x minus 5. A says x minus 1, and it should be x plus 1. So A's out of the question. That leaves us with the answer of C. Number 15. Which of the following graphs represents the function f of x is equal to 2, x minus 3, x minus 1? So it says, which function says this? There are two things we're looking for. Is that a positive or negative? Because it's positive, we know it's going to be shaped up like a cup. We can automatically get rid of B and D. Both of those are down like a frown. Now, we're going to use the zero product property to find our two x-intercepts. We know that this one's going to be x minus 3 equals 0 and x minus 1 equals 0. Add 1 to both sides, and I get x is equal to 1. Add 3 to both sides, and I get x is equal to 3. So I know that it's going to be up like a cup, and both of the x-intercepts are on the positive side of the graph, one at positive 1, the next at positive 3. So which one says that? C has them on the negative side of the graph. A has them on the positive side of the graph, so our answer is A. All right, number 16. That was 15, number 16. what are the zeros of the following quadratic function? What are the zeros? And it says f of x is equal to 1/3 times 5x minus 4 and negative 2x minus 6. The zeros, once again, the zeros are there. The x values when y is equal to 0. So we're going to use the zero product property with each of these. It's going to say 5x minus 4 equals 0 and negative 2x minus 6 equals 0. On this one, I'm going to add 4 to both sides and then divide by 5 on both sides. And I'll get x is equal to 4/5. The decimal version of that is going to be 0.8. On this one, I'm going to add 6 to both sides, and I'm going to get negative 2x is equal to positive 6. Divide by negative 2 on both sides, and I'm going to get x is equal to negative 3. So those are going to be our two zeros. I would accept either one of these, but remember, if it's a point, it's easier to do 0.8 than it is to do 4/5 oftentimes. So the zeros could be done like this, or they could be done like 0.8, 0, and negative 3, 0. It's just the solutions. Okay. Number 17, do I have time? Yeah, I do. Number 17. Which of the following functions could be the function of the graph depicted below? The graph depicted below has kind of this going on. It goes through the origin and it crosses at negative 3. And it crosses at the origin. And we know that it's negative. So for number 17, I'm going to get rid of A and D because both of those equations are positive. B and C have a negative up front. And this is a negative because it's down like a frown. These would be up like a cup. Now, I see my options, and I'm going to use kind of the reverse method that we've been talking about. X is equal to negative 3 and x is equal to 0. I'm going to get both of these equal to 0, right? So I'm going to add 3 to both sides to find out what our original factor is. This one already equals 0. So one of them is going to say x by itself, and that's okay. Then the other one should say x plus 3, which is C. B is out of the question because it says x minus 3. That would occur over here in positive land. Okay, so our answer for 17 is C. Do I have enough time to keep going? This one's a 3-parter, so I'm going to save it for the next video.